We've been talking a lot about differentiability and continuity lately, and this problem's going to expand those ideas, hopefully for you a little bit. So here's the dealio. We got this piecewise function up here, and one piece of it represents this piece of the parabola that I have graphed over here in pink, x squared plus 2x plus 1, for x is greater than or equal to 1. And then this other piece here represents an arbitrary line, ax plus b, and it's defined for x is less than 1. So my question to you is, can you find an a and b value that would make this function continuous? And then, secondly, could you find an a and b value that would make this function differentiable? Maybe they're different, maybe they're the same. Why don't you pause the video and find out for yourself? All right, assuming that you've given it a go, let's begin. Let's first start talking about continuity. Let's talk about continuity first. Continuity. Okay, and let's just remind ourselves what it means to be continuous, and we can look at our piecewise function to talk about it. So we have these two pieces up here. We have this piece of the parabola and this arbitrary line, and we see that there is a potential for discontinuity at x is equal to 1. So in order to ensure that we are continuous, we are going to say that the limit as x goes to 1 of f of x needs to be equal to f of 1. F of 1. And what is f of 1? Well, we can see that our piece of the parabola is defined at x is equal to 1. So we have 1 plus 2 plus 1, which is 4. So as long as our limit as x goes to 1 exists and is equal to 4, we are continuous. And how we're going to evaluate that is with this piecewise function here. We need to check both left and right-handed limits as x goes to 1 and make sure they match and they're equal to 4. So let's do that. Let's take left and right-handed limits. We're going to first look at this piece of the parabola. So the limit as x goes to 1 from the positive side, and we're going to be looking at x squared plus 2x plus 1. Okay, and then our negative-handed limit is going to be the limit as x goes to 1 from the negative side of this arbitrary line, ax plus b. Now, evaluating these limits, as x goes to 1 from the negative side of ax plus b, that's just going to be a plus b. And then up here, for our positive-handed limit, as x goes to 1 from the positive side, we have 1 plus 2 plus 1, which is 4. So we find that in order for our function to be continuous, a plus b needs to be equal to 4. That's our continuity condition, when a plus b is equal to 4. That's our continuity condition. And what is this saying? What is this saying here? Well, this is saying any a and b that add up to 4 will construct a line for us that will make this continuous, make this function continuous. So really, if we were to just give an example here, let's let a be equal to 2. And then b would also be 2. And then we would get this line, y is equal to 2x plus 2. And graphing that, let's see, we got 1, 2, and 1, 2 over 1. Graphing that, we would get a line that looks like this. Looks like that. That looks like that. So again, that's just one example, but again, we have an infinite number of lines that we can construct. Any a and b that add up to 4. So we could also have a line that looks like that. We can also have a line that looks like that. Any a and b that add up to 4 will make this function continuous. So now you can notice when these lines connect, there is a little, they're not necessarily differentiable. You know, we have some corners here. And that's no good. So now we're going to talk about differentiability. We're going to now talk about differentiability because we are going to have a little different story over here. Differentiable. What it means to be differentiable. Grab some more space. Okay. So when we talk about differentiability, again, we're talking about the derivative, and the derivative, remember, is really just talking about slope. So in continuity land over here, we found a condition where we can construct any line that would just simply connect up to this piece of the parabola. And now differentiability is saying, okay, we're going to constrain that a little bit. We're going to constrain that so that when we construct a line, it not only needs to connect up to this piece of the parabola, but when it does so, it needs to have the same slope. So when we find our differentiability condition, we're really trying to smooth out this curve. We're trying to smooth out the curve. Smooth out the curve. That's what we're doing over here. So more formally, just writing out what this would look like, we need our left and right-handed limits as x goes to 1 of the derivative function to match. So we would get the following here. We would need to have the limit as x goes to 1 from the positive side of now our derivative function, f prime of x, to be equal to the limit as x goes to 1 from the negative side of, again, our derivative function, f prime of x. So in order to evaluate this, we need to first find the derivative function. So we're going to do that now. Let's go down here and get the derivative function. And it's also going to be a piecewise function. So again, with this piecewise function here and taking its derivative, we're just going to take the derivative of each of its pieces. So let's do that. Let's grab some more space. And we're going to do that by using the definition of the derivative. We know the derivative. The derivative, f prime of x, is equal to the limit as x goes to some c value of f of x minus f of c. And this is all over x minus c. Okay, so now we're going to apply this definition of the derivative to take the derivative of this piece of the parabola first, x squared plus 2x plus 1. So let's do that, the limit. And again, if you feel encouraged, please pause the video and try to find the derivative function on your own. So going back to taking the derivative, the limit as x goes to c of f of x, which in this case is going to be x squared plus 2x plus 1 minus f of c, which is c squared plus 2c plus 1. And all of this is over x minus c. All right, so now we just need to clean this up and evaluate this limit. So distributing this negative here, we'll see that our 1's will cancel. And then we have x squared minus c squared, which is a difference of squares. So that's going to become x minus c times x plus c. And then distributing this negative, we get a 2x minus 2c. And if we factor 2 out, we have plus 2 times x minus c. Again, all I'm doing is cleaning up the numerator over here. And then we are still dividing by, all of this is over x minus c. So these x minus c's will cancel. And again, we're still keeping the derivative, but save some time, we'll just put those 2 dashes. And we finally get the limit as x goes to c of x plus c plus 2. And evaluating this limit as x goes to c, we get this is equal to 2c plus 2. And that's our derivative. Now, we want to express our derivative function in terms of x, so that's what we're going to do. This is 2x. We want to express in terms of x. 2x plus 2, and again, this is still defined for x is greater than or equal to 1. All right, now we have one more derivative to go. And we're taking now the derivative of ax plus b. So again, we're going to apply the definition of the derivative. So limit as x goes to c of f of x, which is now ax plus b minus f of c. So minus this quantity, ac plus b, all over x minus c. And then cleaning this up, again, our b's will cancel when we distribute this negative. So our b's will cancel, and we can factor out an a. So we have a times x minus c all over x minus c, and we're still taking the limit as x goes to c. These will cancel, and we are left with the limit as x goes to c of a, which is just a. All right, so now we have completed. Let's fill this in. Let's scroll back up, fill this in. We found this to be a, and this is still defined for x is less than 1. So now that's our derivative function, and after we've done all of that work, we are now able to just evaluate our left and right-handed limits. So let's do that. Let's do that. So we have the limit as x goes to 1 from the positive side, and we're going to be looking at 2x plus 2 now, and this is going to be equal to our limit as x goes to 1 from the negative side of a. Evaluating these limits as x goes to 1 from the positive side, that's 4, and that's going to be equal to a. That is going to be equal to a. So that is our differentiability condition. That is our differentiability condition. And real quick here, differentiability, if you can remember, implies continuity. So in order to find b, all we need to plug in is our continuity condition when a is equal to 4. So we find that b is 0. b is 0. b is 0. So these a and b values will make our function differentiable. And that will give us this following line. Y is equal to 4x. And then if we were to come over and plot that, we go through the origin, 1, 2, 3, 4 over 1, and we would get a line that looks something like this. Get a line that looks something like this. And you can see that this line here, when it connects up to this piece of the parabola, it does so in a smooth fashion. And that's because we have the same slope coming into 1 now. So we have this nice smooth transition from this line to this piece of the parabola. So again, don't let the notation confuse you. Continuity is saying, all right, let's make a line that just connects up to this piece of the parabola. And then differentiability says, you know what? I want a little tighter constraint. I want a line that not only connects, but when it does so, I want a smooth transition between the two pieces.